All right. Here we go, ladies and gentlemen. We're going to talk a little bit about energy in reactions. So thermochemistry, one of the big things that we want to be able to look at is how much heat is being gained or released by a specific chemical reaction. Now, in any chemical reaction, you always have some energy that is being put into the reaction and some that's coming out. Every chemical reaction requires some energy in order to be able to break bonds. You also get some energy every time new bonds are formed, and it's proportional to the bond strength. Now, we didn't talk a lot about bond strength when we looked at chemical bonding, when we were talking about things like ionic and covalent bonding, but different bonds have a different amount of strength that's like holding them together. And so if you look here at the two little bullet points that we have, when the bond energy of the reactants is greater than the bond energy of the products, energy is absorbed by the reaction. So this is saying that it takes more energy to break the existing bonds than what you get when you make the new ones. So you have to put more in than you get out. So overall, there is an absorption of energy by the reaction. These reactions would feel cold. When the bond energy of the products is greater than the reactants, then you have energy being released. This means that you're only putting a little bit in and you're getting a lot out, right? So this particular reaction would feel warm. Now, before we can talk about getting too much ahead of ourselves there in terms of reactions feeling warm or cold, let's make some definitions here. System, particular part of the universe that's being absorbed. For us, our system is going to be our reactants and our products. With any chemical reaction. So like the things on the left-hand side and the right-hand side of the arrow as we represent them with the chemical equation. The surroundings is everything outside of that. Now they use this idea of the universe because in theory, eventually all the heat kind of gets spread out all over the place. But we're going to focus our attention a little more locally, and we're going to look at our chemical reactions. Exothermic and endothermic are terms that I hope that you've heard before. Exothermic means that overall you have a release of energy from the system to the surroundings. These were the reactions that would feel warm if they were going on in a beaker. And then endothermic, this is where the system absorbs energy from the surroundings. This is where you would have one of those reactions that feels cold within the beaker. Activation energy curves are ways that we represent kind of what's going on with the reaction. So here's an exothermic reaction. This is one that's going to be releasing energy to the surroundings. Right. So what they're saying here is that the energy required to break these bonds here and to form this little what we call an activated complex or a transition state right here, it's not yet products but it's not reactants anymore. Right. The energy difference from here to here is less than the energy difference from here at the peak until you get down to where our products are. And so because of that, right, this overall energy change from here to here, the difference between where my reactants started and where my products end up, this is how much energy is getting released by the reaction, right? So I have to put a little bit in, but I get a lot out. And the difference between those two is my overall energy change. And so here, the amount of energy it takes, again, to break these bonds, the bond energy here is less than the bond energy here. So we get out more than we put in. Exothermic feels warm, energy released. In an endothermic reaction, it's the opposite. We're having to put all this energy in just to climb up this hill, right? And then we only get a little bit back out, right? So it'd be a little bit like a disappointing roller coaster right here. Like I'm working hard. Okay, the reaction took place and I only got a little bit of energy out of this. And so overall, you're putting in more energy than you're getting out. And so this is one of those reactions where it would feel cold. Not only that, but you'd have to continue to provide energy to this to keep it going. Cold packs would work this way, right? If you put a cold pack in the freezer, the reaction would stop. You take it back out and it would start again and it would continue to be cold. Now that's different than something that's frozen. This means you would actually stop the reaction because you stop giving it energy in order to be able to get up this hill, right? So endothermic, again, bond energy here is greater than the bond energy here. So it's taking more energy to break the bonds than we're getting when we make the bonds. So overall, more in than what we're getting out. It's going to feel cold. Enthalpy is a term that's used to talk about the overall heat change that's involved in a process. And the symbol for enthalpy is this delta H, right? This triangle H. And so for an exothermic process, delta H is negative, which should make sense because if I'm looking at my system, right, it loses energy to the surroundings, so it has less than what it started with, which is why your delta H would be negative. In an endothermic process, delta H is positive, right? And so therefore, you are gaining energy. Your system has more energy than it started out with. You're continuing to pour energy into that thing to keep the reaction going, right? These numbers are going to become more important and more apparent to you when you watch the next video. Hopefully you did it in order when you're looking at thermochemical equations. Bye-bye.